In this video, we are talking about um, rigid bodies and rotational motion and equilibrium under physical realism. So this is the overview. We'll be looking at rigid bodies, translations, rotations, torque, equilibrium, stability, rotational dynamics, and angular momentum. So let's first look at rigid bodies. So these are rigid bodies have a position and an orientation. We spoke about this in the previous video as well, which was on game physics. So rigid bodies assume no object deformation, and these are represented by two parameters: center of mass and orientation. A rigid body is an object or a system of particles in which the distances between the particles are fixed. The distances between the particles remain constant, which means an object to be a rigid body, it has to be solid. However, not all solid bodies are called rigid either. So objects defined in the body space and transformed by the position and orientation into the world space. The body space and the world space. Objects are defined in the body space and then they are transformed by the position and orientation into the world space. So when we talk about rigid body dynamics, kinematics is the study of movement with time, and dynamics is the study of force and masses interacting to cause movement over time. For example, how far a ball travels between a given period of time. Then how far this ball will travel if we hit it with a bat under a force, under the force of gravity. Additionally, for simplification, we are going to model rigid bodies, ones that do not deform. So talking about linear and angular velocity, like we discussed in the previous video, linear velocity is the change of the center of mass over time, while angular velocity is the change in orientation over time. So it has both axis and speed of the rotation. Direction is given by the axis and magnitude is given by the speed. So given a particular vector, we can come up with this equation to represent angular velocity. Then what's a force? Well, we can apply a force to an object at any point. And the total, if there's more than one force that is applied on a particular object, then we can get the total force that is working on a particular object, the sigma of all the forces. Torque. Well, this describes the rotational force. So the total torque on an object can be taken by using this equation, a formula rather, which is there. Now let's talk about rigid bodies, translations, and rotations. So rigid body can have translational motion or rotational motion. Here we have translational motion. It goes in the right hand direction, and it can have rotational motion, like in the second picture. It can rotate, or it can have a combination of both translational and rotational. It can go forward while rolling, while as shown in the third picture. It may roll with or without slipping. So it can have a translational motion or a rotational motion or a combination of both. So for an object that is rolling without slipping, we can come up with this equation. So as shown here, r is the radius and omega is the angular velocity. So we can come up with this equation for an object that is rolling with no slipping. When it comes to torque, equilibrium, and stability, it takes a force to start an object rotating. A force should be applied on the object, an external force should be applied on an object to get it rotating. That force is more effective if it's further away from the axis of rotation. The more it's away from the axis, better it works. And the closer it is to being perpendicular to the line to that axis. If it is perpendicular to the line to the axis, then again it's more effective. The perpendicular distance from the line of force to the axis of rotation is called the lever arm. The distance between axis of rotation and the force line. This perpendicular distance between these two is called the lever arm. Then how do we calculate the torque? It's the product between the force and the lever arm. Force into lever arm is the torque that's working on the particular object. Torque is a vector. It produces an angular acceleration and its direction is along the axis of rotation. So this sign can be gotten through the right hand rule as well, as shown in this image. In order for an object to be in equilibrium, the net force working on this object should be 0. And the net torque on it must be 0 as well. The net force on the object should be 0 and the net torque on the object should be 0. If both are 0, then this object is in equilibrium. If we say that an object is stable, then there must be no net torque working on it around any of the axes. The axis used in calculation may be chosen for convenience when there's no motion. So for an object to be stable, there should be no net torque working on it around any of the given axes. Now, when we come to rotational dynamics, the net torque on an object causes its angular acceleration. We discussed what torque is. So the net torque, when we get the sum of the torque, whichever the way the net torque works, that is the direction of the angular acceleration. So it causes this acceleration. For a point particle, we discussed in the previous video about particles. For a particle, the relationship between torque, force, and angular acceleration is simple than another object. The moments of inertia of a certain symmetrical shape can be calculated. So this image shows an example of how we can calculate moments of inertia of the symmetrical shape. In the simplest case, for a particle, it's I equals mr squared. When we come to angular momentum, it's conserved. In the absence of an external unbalanced torque, the total angular momentum of a system is conserved. The total angular momentum does not change. Internal forces can change a system's moment of inertia. And also its angular speed. An external torque on a rotating object causes it to precess. So an external torque will cause rotating object to undergo precession, just like what's shown in this example. This is a background into rigid bodies rotational motion, translation, torque, equilibrium, stability, and angular momentum. In the next video, we'll talk about soft bodies.